So, hi, I'm Jenny. I've been here since 2000. I don't know how that happened. And I'm glad that everybody could make it through the cold. Hopefully the talk will be entertaining enough that we'll all warm up. Joe actually asked me to speak, you were standing here, on creativity. So I found a way to bridge a bunch of the basic work that I've been doing in creativity and the methods that we use to look at creative thinking with also some work that I've applied a creative thinking task in an educational context. So hopefully you can see the thread that's going to underlie the work. How do I make it go? Like
press space bar.
Okay.
From above.
He is my God. Okay, so how do we think of new things? Human cognition is amazing. As humans, we're capable of learning a vast vocabulary of words. We can recognize thousands of paintings, faces, scenes. Another amazing attribute of human cognition is our ability for creative thought, for innovation and invention, the ability to think of new things. So how do we think of new things? How are we able to find new uses for old objects? Inventor George Mistral was taking a walk with his dog in the woods near his house, and when he came home, his dog and his pants and his sleeves and his socks were all covered in burrs. Surely this is not the first time he had ever taken a walk through his property and gotten burrs on his clothing. But on this day, he saw them in a new light. What invention do you think this inspired?
Velcro.
Velcro, yes. So the creative idea was Velcro. And what allowed him to take this everyday occurrence and put it into a new context? This is something we can think of as an example of creative thinking. So some things I'll be addressing today are, first of all, some methods and measurement in the studies of creativity, and some questions that I'm going to be focusing on as we go through the basic studies are what limits creative problem solving, what improves creative problem solving, what effects do examples have on creativity, and like I said, we're going to end with an application to an educational context. Today, I fought with PowerPoint frequently about making creativity have a small c. It really wanted creativity to have a large C. So the connotation is large C are the works that Picasso has created, the work that Mozart has created. I am not studying that. I cannot go out and find the next Mozart or Picasso. What I can study is small c creativity. So these everyday acts of creative thinking in which we come up with ideas that are novel in some way, so they're unexpected, they're unusual, they're atypical, and they also have to have some value in some way. So just being absurd for absurdity's sake is not necessarily creativity. There needs to be a balance here between finding something remote, novel, original, and it fulfilling some goal. So let's all solve this problem, right? So if we rely on our past experience, we can use a formula that we may have in mind, and we know, okay, to find that hypotenuse, I'm going to do a squared plus b squared equals c squared. And I can even remember to put the 3 and the 4 in the right place, and I can come up with their, is that at the square? Yeah, that's the square, okay. And then take the square root of 25, and I find an answer. My answer is 5 equals x. Here's another solution, that if your goal is not coming up with a correct mathematical answer, then this is a perfectly fine solution if your goal is humor, and humor can be a goal. So this is a creative solution that we can see an original, unexpected, atypical answer, and it fulfills my goal of humor in a talk. We can also see linguistic creativity. So speakers use metaphor and analogy, novel expressions to draw their attention to a point that they're trying to make. You can see creativity in novel uses for objects. So there are a lot of different ways that we can see creativity in our world. The approach that I come from is an information processing perspective, and so I'm going to study creativity with a little c, by thinking about how it results from normal cognitive or memory-based processes. So my goal is to try to identify specific processes that may underlie or prevent creative solutions. And you can think of this as reductionist. I don't think of that as a dirty word. Like, we are trying to come up with what are the smaller parts within this larger construct of creativity, instead of me going out and trying to analyze Mozart or Picasso. What are the smaller steps that I can see that allow us to come to novel, original, and useful ideas? And I can try to break it in to the specific sub-processes that I think might go along the way. So in order to come up with ideas, we need to generate them. Where are they going to come from? A lot of the time they're coming from memory. That's where we're getting our ideas from our long-term memory. I may notice connections, and that could help me retrieve things from memory. I may elaborate on ideas once they're retrieved from memory. I may engage in applying ideas in a novel circumstance or combining it in a new way. And then there's always this evaluation phase, which we actually tend to not study too much because it's so difficult. But if you think about it, so much of creativity is actually like building on your hunches. So you're going through an unconscious evaluation process of censorship, even when you're coming up with ideas. So evaluation is pervasive from the very first thoughts and associations that we're trying to get out of our long-term memory, all the way through to recognizing capital C creativity, which relies on not just your own evaluation and your own efforts, but then the recognition of the public and others and critics. So it's evaluation on all different levels that can be a filter for creative ideas. So why is it so hard to reach these creative solutions? Here are some basic premises. The most accessible approaches are generally the ones that are most common and routine. So as we're retrieving things from memory, we're necessarily going to come up with less original ideas first. We also generally impose assumptions or constraints, which most of the time help us. When you're trying to solve a math problem, assuming it's a math problem is usually a good idea. It's just in a couple little tricky circumstances that thinking outside the box and thinking about the problem in a new way might actually be more beneficial. So imposing assumptions or constraints can limit the number of solutions that we consider. That's usually a good thing, but when you're looking for a creative or remote solution, it may be putting you in the wrong part of a solution space. So we need to overcome these obvious ideas or usual approaches and move past them. But unfortunately, these are the things we get stuck thinking about. So the term that we use for being stuck is fixation or mental fixation. And it's been studied for a long time, primarily by the Gestalt psychologists. It's been demonstrated in a number of ways. So here's the two-string problem, which is not drawn very well, but the problem itself is that you have two strings hanging from the ceiling, and your goal is to tie them together. But the two strings are actually so far apart that you cannot reach them with both arms at the same time. So that's why this drawing is misleading. So just imagine that he's much further away from that second string. Using only what is available in this picture, what can you do to get those two strings and tie them together? Yes? Either of you, both of you.
You can stand on the chair and take one of the strings down, and then...
Ooh, awesome. You get a point. Do you have another answer?
I was going to say you can stand on the chair because they could probably reach if they're like right along the ceiling.
Definitely worth a try. Other answers?
I'm not sure if I heard this. I would just pull the strings down to tie them together.
Just pull them down all together.
Yep.
Okay, everybody's thinking outside the box. Any other answers? Okay.
Grab the pliers and use them to pull one of the
Thank
strings
you. As Meyer wanted, that is his intended solution, that he wants you to use the pliers as a pendulum. And once you've tied the pliers to one string, then you can swing it. But these were great answers. My all-time favorite answer is taking off your pants. I could not find a picture of this. One day I will draw it. But tying one end of your jeans to one string, and then you can reach it to the other string. Okay. Another example, here's Dunker's candle problem. Your goal is to use these objects, so you've got a candle, a book of matches, a box of tacks, and a corkboard, and you need to affix the candle to the wall so as to illuminate laboratory experiments. Susan, you've seen this before.
I haven't ever heard the last part of illuminating.
Yeah, no, that's the old-timey phrasing. Yeah, so any ideas on this one?
Just need to put wax on something and then it'll stick.
Yeah, so that's the first one, is like either trying to like melt the candle into the tacks, or in some way trying to stick the tack into the candle and then into the wall. That doesn't actually work. How about we think outside the box?
What are you popping in?
Yeah, can you repeat the resources and
Sure.
goals?
Book of matches, box of tacks, and a candle.
I'd connect the box to the wall with the tacks and put the candle in.
That's awesome, and that is literally thinking outside the box, which may or may not be where this expression came from, but that is Dunker's preferred solution, was that when the tacks are in the box, you see the box as a container. There's another iteration of the study where the tacks are just on the table and the box is sitting there. Many more people use the box as a shelf when it doesn't have the tacks in it. Okay, so there you go. There's our answer. So clearly, it's easiest for us to think of objects in their common use. We tend to focus on typical functions. So we don't think about pliers as a weight. We don't think about a box as a shelf. And this constrains us when we're coming up with creative solutions. So there are other tasks that we've used in the laboratory instead of these sort of one-shot puzzle problems. We try to come up with sets of problems that each share that characteristic. So this is called the remote associates task. Here what you're trying to do is come up with a fourth word that forms a good English phrase with each of the other three. Yay, cheese! Blue cheese, cheesecake, cottage cheese. So that's how the task works. Here's another one. Plate, broken and shot.
Glass?
Glass. So plate glass, broken glass, shot glass. If you have a lot of baseball expertise, you may have tried to use home. So home plate, broken home, that goes okay. And then shot home, home shot, not so good. So baseball expertise on these problems is actually misleading. And so this is an example of how in creative problem solving, the solution that comes to mind first, even though it may be primed by our prior knowledge, we can get stuck in it, and then it makes it harder for us to find these remote solutions when there's a misleading association. So we can also bring misleading associates right on the same screen. So instead of relying on prior baseball knowledge, Steve Smith has used just putting associations on the screen at the same time. So shock, shave, and taste. Because it has those associates right on the screen, makes it really hard for you to solve. So don't say it out loud, because I'm going to let you all think about that for the next 40 minutes. Okay, so one approach from creative problem solving is what I would call the creative problems approach, and it really relies on coming up with a special set of problems that have a characteristic that we're interested in. We're looking for problems that lead people initially in the wrong direction, whether it's because of the assumptions that they make about the objects in the problem or the associations to their prior knowledge. It's a specialized set of problems that are highly likely to bias people towards an incorrect solution, so an incorrect space or an incorrect problem representation. And oftentimes we try to compare these sets of problems to more routine problems, and those tend to be long division or other basic math that we're fairly certain that people know how to do, and the way that they tend to solve them is just by going through steps. So we try to contrast a more routine or analytic kind of problem solving against creative problem solving, where you need to get past an initial solution and think of something more obvious, less obvious, more novel. And then the main dependent variables in these types of studies are just simply the likelihood of reaching a solution or the solution time. And so fixation would be if you see fewer people solving the problem or see them taking longer to solve it. Okay, we can also see fixation in tasks that we call divergent thinking or idea generation tasks. So these are based on work by Guilford, where it's just a very simple task. You can do it paper and pencil, you can do it just speaking out loud, and you say, come up with as many creative uses for a tire as possible. Another alternative are design tasks, where you ask somebody to design something, in this case, a spill-proof coffee cup. And in this task, they need to design something. So these are both creative generation tasks. One is just simple ideas, the other is a bit more complex because you're actually designing a product. Even though this alternate uses task is very simple, people are just generating ideas for everyday objects, they're very unlikely to produce novel ideas.
Mm-hmm.
So they default to these known uses. So, driving, somehow using it on a car. They produce ideas based on what they know, so things that you see every day, tires are used for. And they need time to get past those initial ideas. So we see something like this increasing function where the number of original ideas that you produce in your first few guesses is very low, but as you move on, you can start to get more creative. Brainstorming with others. So the interesting thing is that the prevailing ideas in the literature are that brainstorming with other people doesn't actually help things. It ends up interfering as much as it helps. So that's sort of this prevailing assumption that it may make things worse because it activates a lot of inappropriate information that ends up blocking your originality. You can also see fixation in design tasks. So engineers and undergraduates are asked to design, in this case, a measuring cup for the visually impaired. And they're shown this example of a measuring cup where you, like each bin is a quarter cup and you click to know how many quarter cups you're using the measuring cup for. And what happens is when they're shown this example, they end up producing designs that conform to the same flaws that are in that original example. So imagine if you're blind, you probably need to know when you're adding too much liquid to your measuring cup. Overflow can be a problem. You can't see that it's going to overflow. And so when they're given this example, there's no overflow device in the example, and many more people that are shown the example also have a problem that they don't have an overflow device. The other problem with this is that you don't always need to measure only in increments of a quarter cup. You may want to make something that uses a different increment. And so in this example, you're constrained to the quarter cups. The new designs had that same problem. So people are incorporating features of example ideas into their own generations. We don't know whether they're doing it intentionally or unintentionally, but this is a common occurrence. It happens for measuring cups. It happens for spill-proof coffee mugs. It also happens when you ask people to design aliens. Ask any kid to design an alien. How many eyes do they have? 2. How many legs do they have? 2. Do they keep symmetry? Their aliens end up looking like humans with green, right? Or blue. Blue's the new alien color. Toys, the same thing. When you show people examples of toys or when you ask them to design toys, they end up coming up with designs that are very similar to toys that they already know and love. Okay, so we've seen a little bit about what limits creative problem solving. We have a little bit of a sense already that example ideas are not necessarily always going to help. Like there's this intuitive feeling that giving people examples might get them started on a track, and yet we've seen a bunch of studies showing that example ideas can be harmful. So one thing that we pushed on in our studies was asking, do examples always need to be harmful? So an original study by Smith, Ward, and Schumacher asked undergraduates to design new toys. In one condition, they saw 3 example toys that shared 3 features: a ball, a physical activity, and electronics. So in the first example, this toy combines exercise and fun for one person. the score counter electronically keeps track of the number of hits of the rackets. So you've got 2 rackets, and you've got a counter, and you've got a ball. The second example over here, this toy combines exercise with fun. Use the remote control to choose the action. And so I think that's a football coming out of a chute, and so it's basically a bag of footballs, and it goes through, it basically shoots out at you. Or I don't know whether they're shooting the football or whether they're catching the football. Something is happening with the football. I guess the arrow makes it seem like the football's coming out. Okay, finally, the bottom one, this toy combines exercise with fun. The fields build up as the bikes are pedaled, and the goal is to push the ball toward the opponent. So this one feels a little Dr. Seussical, right? Like you can imagine that they're pedaling on bikes and it's pushing the ball to each other. So participants that see these 3 examples are more likely to include these 3 features in their new toy designs. And so this and the original study was evidence of fixation. They were conforming to the old examples with their new designs. But a question that they didn't ask in that original study is whether it actually reduced the perceived creativity of the designs. And so that was the goal of this experiment, was to actually test whether or not the perceived creativity of these designs would be increased or decreased by example exposure. So in the first study, we exposed people to examples, and then in the second study, already assuming that examples are going to harm something, we give them a warning, pay no attention to those examples. So experiment 1, they see the examples or no examples, and they sketch toys. We score the number of the 3 features that all the examples have. So do these designs have a ball in them? Do they involve physical activity? Do they have electronic device? So this is 0, 1 scoring. You use 2 coders, and then you get inter-rater reliability to see whether or not everybody is noticing the same features in the toys. For creativity, we used a subjective judgment of novelty. And so this was, how novel does this toy seem? And we didn't define it, we just let people decide on a 1 to 5 scale how novel it seems. So again, subjective. Here's an example toy. So this is the best toy that we saw. This is sort of like a Bop It kind of toy. So let's go over here. So this toy is a ball that can be played with numerous people. However, the ball must be caught by one of the sticks. The safe sticks will not splash anything at you. But if you grab one of the not safe sticks, then a disgusting substance will cover you from head to toe. So basically you've got a mud stick, a booger stick, a moldy stick, and a goo stick. Those are the bad sticks that will cover you with those substances. And then the safe sticks are just the plain ones that don't indicate what gross substance they have on them. So this does have all 3, or at least 2 of the example features, right? There's some physical activity and there's a ball. But the raters thought of this as very novel. Here are some other examples. Okay, so Rubik's Cube. Low creative, low example features. It says, what I've designed here is a Rubik's Cube. The second one, low creative, high example features. It's basically a basketball game, and so it's got a ball, it's got an electronic counter, it's got physical activity. So you can see it's got high conformity, but it's a basketball game. And then high creative, low example features is the little psychotherapist. So it's a doctor's kit specifically for psychotherapy. I think it has Xanax in it, and the DSM. So no ball, no physical activity, no electricity, right? So none of the example features, but this was seen as very creative. Okay, and this is what happened. So the first thing to look at are the dark red bars. And you can see that when we show people examples, we replicate the earlier finding that seeing those examples makes you conform to those examples. You put more of those features in your design. However, it didn't hurt their novelty, right? So that we're giving them examples, there is conformity, but it's boosting their novelty. Okay, so then we follow up. There was another study in the original Smith paper that included a condition with a warning. In their study, warning did not reduce conformity. We want to know what effect will that warning have on novelty. So same study, you can see my little arrows already there. So this is now the second experiment data with the warning. The things to notice are that the dark red line is where conformity was without the warning in experiment 1. So the difference between where the red bar in examples is here and where it was in experiment 1 is saying that we are reducing conformity by giving them a warning. So they're doing what they're told. They're not putting as many of those examples in there. But warning didn't do anything to novelty. So having seen the examples and now being told to ignore them looks very similar. The dotted line is the result from the last time. So it's neither improving novelty or reducing novelty. Okay, so example ideas are not always harmful. There was evidence for conformity with the examples, but that didn't undermine the perceived novelty of the toy designs. So there are a bunch of reasons why these examples might have improved ideas. So first of all, most of those examples that led to poor results were because the examples were flawed. That measuring cup already had the flaws in it, and so the toy examples don't have a flaw in them. Also, it feels like the examples may have helped jumpstart creativity. Toy invention is a very open and unconstrained task, so it may actually be overwhelming to not have examples in that task. So this could have helped people get started on a track, and it helped them to constrain the search space a little bit, which ended up making them more novel. But another important methodological point is that the coding for creativity in this study was subjective. We were using raters' impressions of the novelty of the toy designs. And so we want to test and see whether or not we find the same or different effects when we can use a paradigm where we have a more objective measure of novelty or originality. So now back to our tire and the alternate uses task. You need to come up with as many uses for a tire as possible. And our question is, do examples harm here? Having the common ideas are the ones that are going to be the easiest to retrieve from memory. Exposure to common ideas could increase your fixation, and it could impede your novel idea generation. So here are the top 5 uses for a tire, according to UIC undergraduates in 2017. Tie a rope to it and make it a tire swing. Yeah, that seems pretty common, right? Use it as a chair. Not as common to me, but fine. Use it as an exercise tool by lifting it. This was the height of the tractor tire craze, apparently. Get inside it and roll down a hill, and then plant flowers in it. So depending on how close you live to trailer homes, like I'm used to seeing tires used as planters. Sometimes they're painted. I don't know if this counts as creativity. But these are our top 5 uses for a tire in the United States. And can seeing these common examples, what are the conditions that we think seeing these common examples might actually stimulate better performance? Well, maybe this is when you need the warning, right? That when you have these common examples, maybe knowing to avoid these common ideas might help you towards more novel ideas and help you stop wasting time getting stuck on the common ideas. So you can just sort of skip past the novel one, the typical ones. Listen to what I mean, not what I say. Okay, so here's a nice novel one, right? I think that's so cute. Okay, so do instructions encouraging people to avoid a list of unoriginal ideas help people to generate more original ideas in the AUT? I'm going to give you 2 possibilities. One is the fixation account, that exposure to common ideas may fixate people and impair them. Or, on the other hand, the direction account, that knowing what to avoid may guide you toward more novel ideas. So here's the design. It's a 2x2. They either get these 5 most common ideas, the same ones I showed you before, or they get none of those ideas. So just type all of the original and creative uses for a car tire you can think of. Or here are some example ideas and try to avoid them. Sorry, this is not really good. No avoid instruction. So this one has no avoid instruction, and then the final is some people get just the avoid instruction, but other people have gotten what the things to avoid are. Sorry, that was not very clear, but nod, like, does it, okay, thank you. Oh, so fixation account, example, exposure is going to reduce originality, direction account, that the examples plus the avoid instruction, so this green box should lead to highest originality. So that would be an interaction. Here's what it would look like visually. So if you think about bar graphs, if we see fixation, then just being exposed to those examples is going to lower performance overall. If there's a benefit from having seen the common examples plus the warning, then we get this interaction. One of these bars is not like the other, and we're expecting to see the interaction in our analyses. How did we score these? Okay, so now we can move from a subjective approach to a more objective approach, where we can actually look at the frequency of uses that people generate in our corpus. And we can say objectively, if only one person says to use attire as underwear, that is a very uncommon or original response. Whereas if 24 people say to use attire as a planter, that is a more common response. So here are some example ideas: flotation device, storage container, obstacle course. Original ideas: hang it as a chandelier, wear it as underwear, preferably for males. And a ring for a game of Quidditch. And here's my Google art that is the closest I could get to underwear for males. We're going to look at one other dependent variable, and that's going to be this graph of whether or not there's a change in the likelihood of original ideas over time. If examples are fixating, then we should see a really flat effect. However, if we are able to get over fixation, then we may see this increasing slope. Okay, so for you, it goes this way. Flat or slope. Okay, so here's what happened. The thing that should pop out to you in this bar graph is the interaction. That when people got the warning and the examples, there was a larger number of highly original ideas in their responses. We can look now at, in all four conditions, there's actually not much fixation. Everybody is able to get to these original ideas over time. So in this study, not so much fixation, and if anything, improvement by being able to know what the common examples are and being warned to move past them. Okay, so does seeing what to avoid help or hurt? Now, instead of giving them a verbal description of what not to do, we're giving them pictures. So it's a picture of a tire swing, a picture of using a tire as a chair, a picture of using a tire to exercise, a picture of rolling down a hill in a tire, and a picture of a tire as a planter. Prior work suggests that presenting objects in a visual modality can restrict creative thinking. So visualizations are very powerful, and they may bring to mind movement, gesture, action. Like the fact that it's presented in a visual modality helps us to connect with the normal way that we use and imagine using an object. So it's going to make the typical function of the object more salient. So it's an interesting question whether exposure to these visual depictions of common uses is going to cause fixation and impair originality. And if so, will the avoid instructions help mitigate that fixation? So here it's the same exact design. The only difference is that we're showing them the photographs for the uses instead of the verbal descriptions. Same exact hypotheses, right? So if the visual examples are hurting them, we expect this main effect, that the two bars when you have the pictures are lower than when you don't, whereas the direction account would suggest we'd get this interaction. And what we get is an interaction, but not the one we were expecting. So here what's happening is that when you have visual examples, so that open white bar without the warning, now people are more stuck. But if you give them the warning, then they're able to get over the fixation. But it just brings them back to where they would have been without the examples there. So now there's no longer a benefit from the examples. There's a harm from having seen the visual examples, but you can ameliorate it if you give people the warning. We can see the same result in the slopes. So here in the top, we have the no examples. That's the slope showing that they're getting more creative over time. In the bottom, when they have the visual examples, these are more flat. So there is more presence of fixation when the visual examples are given. Okay, so we see some contrasting effects for visual and verbal examples. For verbal examples, the results support the direction account. So instructing people to avoid the common ideas are boosting originality. However, for the visual examples, we're seeing fixation, that the mere exposure to visual examples hinders originality. And this, of course, suggests there's something especially powerful about visual depictions. So an important take-home methodological point is that we need to think carefully about what kinds of examples we provide. Okay. So creativity and memory are closely connected. We rely on retrieval of old ideas to build new ideas, but the contents of memory are sometimes not conducive to more creative problem solving. We're biased by our experience, we're biased towards common ideas. These are generally good things that help us come up with what's most likely to be needed in a situation. But in the case of creative problem solving, it can lead to fixation on the first ideas that we consider. And we've also seen that examples are not always helpful or harmful, and we need to think carefully about the ideas that we provide. So I promised that we'd talk a little bit about how we can overcome fixation and what conditions might actually help improve creative problem solving. Okay, now try this remote associates problem again. Shock, shave, taste. After. Did you have it before? Popped in your head now?
I've been thinking about it.
Oh, fine. So not exactly unconscious incubation, but still, there are several manipulations that are thought to improve creativity by reducing activation of irrelevant or competing information. One of those is switching between tasks or contexts. Another is taking a break. And so the bed, bath, bus syndrome is when anecdotally many people say that they have their best ideas. When you are in that like half wake state in bed at night or in the middle of the night or waking up in the morning, when you go to take a shower, when you're stepping on the bus. There are these like moments that you stop thinking so closely about the problem that you're trying to solve that allows you to take a new perspective, allow new ideas to come in. We can also see the same theme in individual differences. So our attentional control can keep us focused on solution paths. And those solution paths that are fixating are ones that are primed by our prior knowledge, primed by our prior experience. If we have high working memory capacity, good ability to control our own thought, then it can actually keep us stuck on those wrong answers. So high working memory individuals are less likely to escape fixation. Low working memory individuals are more likely to give up on an analytic approach and are actually better able to find shortcuts when they're solving problems. High working memory individuals are more likely to have mental set in the first place. So again, working memory is something we generally associate with better problem solving and better cognition. But in this particular circumstance, it could keep you stuck and focused on the wrong information to solve the problem. Other ways of getting rid of too much focus, getting older helps. I'm much more creative now. Humor helps. Working at a non-optimal time of day, so if you usually work in the morning, coming back to something in the evening. And just, 1 or 2 beers can also help to shift your perspective. And the mechanism is that all of these conditions are helping to broaden the scope of your attention and allowing more remote or unlikely possibilities to gain activation. Okay, so a few other things that can broaden the range of ideas: taking a walk. 30 physically or mentally, so mind wandering also helps to activate remote associations. Living abroad is a good thing. Being bilingual is a good thing. And finally, collaboration. So I now want to return to the tension that we've seen in the literature having to do with whether or not collaborating or brainstorming in a group can lead to creative products. So that's one debate which is sort of couched in the social psychology area, whether or not the products of groups can ever be better than the products of individuals. Another tension within the education world is whether discovery learning can ever be better than direct instruction. Or, if you're on this discovery side of the debate, whether direct instruction can ever be better than discovery learning. Now, obviously, these are extreme positions, and the answer is always going to be when and for whom and under what circumstances. But just to set up the contrasting sides, a direct instruction approach would suggest that solving problems with a corrected formula from the beginning, so that you're always solving it correctly, is going to ensure that you don't introduce errors into the learner's mind. And so therefore, that's going to be a more effective way of teaching a student an approach. Also, people claim that direct instruction is going to be best when students have no chance of discovering a correct formula on their own. The challenge to this is that reaching particular impasses and discussing multiple representations or multiple approaches can have benefits in itself. So knowing what doesn't work, knowing what leads to failure, knowing alternative ways of representing ideas can end up having benefits downstream. And so people have been using what I'll call invention activities to look at how we might teach students about standard deviation. So the formula that we use for standard deviation, at least in psychology, is that you're looking at differences between observations and a mean squared, and then you take the square root. So nobody is going to come up with that on their own. Like it's not an approach that you would come up with on your own. And so you could say, oh, direct instruction might be better for this. However, we already know that activities that have helped students to learn about standard deviation have been successful. And it's actually the lesson that I've seen the most invention activities around. And so Manu Kapoor refers to this as productive failure. Vincent Levin, Ken Kinninger, and Ida Roll call it invention activities. And then Dan Schwartz, who really started this all in his work with John Black, called it preparation for future learning. So, interestingly, these invention activities are also put in a collaborative context. So it's not a single child inventing, but it's students working in groups to invent. So why would collaboration improve creative problem solving? Well, the presence of others, although it may be distracting, also has the possibility of contributing slightly different perspectives from each of the members of a group. It may help us get around individual cognitive capacity limitations. And it could help to promote abstraction, reflection, justification, explanation, all of these activities that we believe are helpful for helping people to refine their own understanding. A final question is whether group composition might matter. When we put kids together in groups, should we be striving for groups that are homogeneous or heterogeneous? From the social literature, there's a lot of benefit that happens from working with people that you consider yourself similar to. There are fewer what they call transaction costs. You're able to convey your ideas to someone else much more easily. So they prefer to work with people that they consider similar. They choose to discuss the information that they share. They have fewer communication costs. They construct shared representations more easily. And all of this suggests that groups that have common backgrounds will be more effective. But you can turn each of those on its head, that sometimes some difficulty in coming to a shared representation is actually what you're looking for, because that helps you to understand your own understanding or your own representation better if you have to try to explain it to someone else. So if one of the presumed advantages from collaboration is this ability to pool information or to have diverse perspectives or to have multiple people trying to contribute to a shared representation, then having diverse knowledge may ultimately be more effective. So all that I think will play out a little bit as we go through this data of what are the contrasts that I'm trying to set up. So this is the problem that Michael Wiedemann came up with. It was about tea and variability in tea growers. So he was very interested in tea. And so this is a problem that you've got Thurbo, Darian, and Ging, and we want to buy tea from the tea grower that has the most consistent levels of antioxidants. So this is all about having students approach the problem of how to come up with a method to assess variability or assess consistency. For those of you that read the paper that I sent before, there were 2 studies in there. This is going to be both of them sort of mushed together. So you know that we started by asking people for a formula for consistency, and undergraduates yelled at us. They did not want to come up with a formula. And so we said, okay, come up with a method. And then they were fine. And then more than half of them gave us a formula when they came up with their method, but just like it was so intimidating to say, come up with a formula. So this is the softer approach. Your task is to come up with a method to show which tea grower has the most consistent levels of oxidation, antioxidants. They're all instructed to first make histograms of the antioxidant levels for each tea grower and then come up with a method. So we did some sneaky things in here, right? So the different tea growers have different numbers of observations. So now you can't just use a sum, you have to use an average in some way. We also made it so that the average for each tea grower is 15, so you can't use the mean. And this pushes you to start thinking about other aspects of this data. So we've got 127 undergraduates. I'm collapsing across studies. They end up in 45 face-to-face triads. The way I manipulated, or the way we implemented cognitive diversity in this study is by math skill. So we just took their math ACTs and did a median split and whether or not people were low or high. And there were 3 triad types. Either all 3 of the students were low in math ACT scores, all 3 of them were high, or mixed. So that mixed group is the really important one for testing the diversity hypothesis. The quiz that we gave them after they did the green tea activity, so they do the green tea activity, then we actually do teach them about standard deviation. So that's where this preparation for future learning comes in, is that we're not expecting the result of that green tea activity to be to actually know to square and take the square root. Rather, we give them the lesson after they've already been through those difficulties and they can now see what the usefulness of this formula is. But then later they take a quiz where they have to use that standard deviation that they learned about and a transfer question where they now have to create standardized scores. So they're both applying the standard deviation that they learned about and putting it in a new context with standardized scores. So we're scoring that quiz based on coding that other people have used. It's basically 4 categories. And importantly, we do what's called an interclass correlation where we test whether or not the members of those groups end up being independent. For most of your statistical tests that are done on individuals, there's an assumption of independence, that each person is independent. But when kids are learning in groups, you have to ask, is it better to represent that data as a group because all 3 kids perform so similarly? Or is it okay to still consider that the student's quiz score represents a student's performance? And so this is a statistical way. We're not going to get into philosophy or theory, but just a statistical way of showing whether or not those observations are independent. So in this case, the ICC is very low. An ICC of 1 would mean that all kids in a group scored exactly the same on the quiz. So this is close to 0, and it means that we can proceed with testing the quiz scores as individuals. We also coded their worksheets, so everything is done paper and pencil, so we have all of their worksheets as they're coming up with this method. And because that's done at a group level, we only have 1 of those for each group. And there are 22 different solution approaches, which I'll show you in a second. So here's fun stuff. These are the drawings that they came up with as they're trying to figure out their method. So everyone needs to do histograms. Here's an example of one group's histograms. And you can see there aren't that many cases, but what this group has done is first they look at the cases, then they compute where the mean is. And you can see the mean for all three is 15. And so that's like, not everybody computes the mean. Most of them do as their second step. So most of them start with the histogram, then compute a mean, and they're like, oh, it's 15. All of them are 15. We can't just do the mean. So then they start to talk about other things. And so while these graphs and inscriptions and sketches are not the method in themselves, they're giving them key insights into variability. So like there are kids that as they're drawing this, they're like, how do I get the ups and downs? This is another, like the roller coaster, like what are the ups and downs? This is, looks pretty, but is completely wrong. Drawing a regression line here does not help you. Here you can see a group finally getting that it's not about the differences between adjacent numbers, but it has to be a difference from a mean that matters. And then, of course, the best group is the target group, in my opinion, because here 15 is at the center, and they're looking at the distances that the scores are from 15. So beautiful. So we coded their talk as well as what they're writing down for what we see in terms of the 22 different solution approaches. Everybody gets the graph histogram, but then how many of these other approaches do we see? So for solution approaches, what should pop out to you is that in these mixed groups, they're considering over 6 on average of those different 22 approaches. So having a mix of high and low math ability is better in terms of the number of solution approaches that they're considering than having all high math ability students.
It's just a technical question about their triads. How did you balance low and high?
We didn't. So basically, they came in and they were either all low, all high, or any kind of mixed. So sometimes it's too high, sometimes it's too low.
Was there any difference between?
I don't think so, and I think the ends get really small at that point. I really don't think there was a difference though. So that's really fun, right? That we're seeing, like, who would have thought that a mix of high and low math kids in a group are going to come up with a richer discussion than a high math group? Okay, maybe you would have, and you're very smart, but I think this is really cool. And then when we go to the quiz scores, we can also see the benefits are happening there. That when all high students, the high students are going to do well, regardless of what you do to them. But when you put the low students into the mixed group, they're gaining, and even the high group are gaining on the quiz scores from having been in this mixed group. Okay, so, and then this is just the mediation analysis showing that those two patterns that we saw that were very similar, right? The groups that are coming up with more diversity in their representations are doing better on the quizzes. This is showing that it actually is those same groups. So there is this path that's going from what the group is doing to how many representations the group is discussing, finally to their learning or their quiz performance. So what I'm hoping is that you think that these results suggest a real value from engaging in creative problem solving in this educational context. Students who are told the correct formula as part of direct instruction, we don't have that condition in this set of studies, but they most likely wouldn't be engaging in this exploration of the different possible representations. And we wouldn't expect that they're going to show the same benefit on another task that requires them to really understand variability or to have a sense of it from multiple representations. So I think there are a lot of exciting opportunities to test how and when students benefit from creative activities. We also, I didn't have the N in these studies, so we don't have direct instruction conditions in most of them. We also don't have individual problem solvers in most of them. So those are two really interesting comparison conditions that we might want to see. And at this point, I don't know whether or not learning by invention is a creative problem solving advantage, or is it a collaboration advantage, or is it both? And I don't know yet. And that's probably the end. Good. Thanks.
Cool.